Okay, so in this video, we're going to start talking about new numerical measures for how to describe a data set. And we're talking about the most important one later on, the standard deviation. But the first thing we're going to talk about is very simple. It's the range of a data set, which it's just the distance between the largest and the smallest point. We probably used this already when we found frequency distribution. We had to, if we want to do, if we are given a number of classes, then we need to find the range, divide by the number of classes to find the width of each class, right? So we already found a range when we did that. It's just the difference between the largest value and the smallest value. So if I have, in my example, 10 students, and I want to find what the range of this data is, the largest is 93, the smallest is 45, so the difference between them is 48. This gives us another snapshot of the whole of the data, right? Imagine I go to the coffee room in my workplace, and I cross over with a colleague and I say, hey, I just gave back my first exam and the mean was 72. Okay, that gives them one snapshot, right? That was a measure of the center, what was the average score. But if I tell them nobody got above 80, right? That gives you a whole different perspective. If I give you both things, the mean was 72 and nobody got above 80, it gives you a lot more insight of how the data, how the results of my exam were, right? So the range gives us another big insight. But the second idea to talk about how the data is distributed is this idea of having how far are an average each data from the mean. So this is going to be the idea behind the variance. So before we got the variance, this is going to be something different. We're going towards the variance. But right now, pretend to have a very simple data set with only 5 numbers, 6, 6, 8, 10, and 15. The mean of these numbers is 45, right? 6 and 6 is 12, and 8 is 20, 30, 45. So divide 45 by 9. So the mean is, 45 by 5, and you get 9. So I want to find how far is each data set from the mean. Yeah, so I would do xi minus the mean. So I would do 6 minus 9. That will give me a negative 3, right? Another 6 minus 9. I'll have another one with negative 3. But the 10 minus 9, for example, would give me a positive 1. And the 15 minus 1 would give you a positive 6. So these are called the deviations. So if I wanted to know, in average, how far are the data from my mean, the problem is that I would want to find the average of these values. But the problem is that if I add them, I'm going to get a 0. Check. I have negative 3 plus negative 3 is negative 6 plus a negative 1. I get negative 7. And these two together are positive 7. So I get a 0. Yeah, that's always going to happen. Let me write it down carefully to see what is going on. So if I write this, how I got this, how I got the first negative 3, I got 6 minus 9. How did I get the second negative 3? I got another 6 minus 9. Well, I could put a parenthesis here. That's how I got my first and my second deviation. But I really don't need those parentheses, right? They're just in the way, so I can just ignore them, right? So I'm going to do plus 8 minus 9. That's the negative 1. Plus a 10 minus 9. And plus a 15 minus 9. So look what happened. I have here 1, 2, 3, 4, 5 times the mean, right? 1 per each time that I added one of these deviations. And so 5 times the mean just gives me the total sum. Remember when I added these numbers, I got 45. So before I divided by 5, I get 5 times 9. So those negative 9s together are really negative 45. But when I add the positive number, when I add the 6, when I add the data values, that's exactly what I got. I got a 45. So of course that's going to be a 0. So nothing is special about this data set. That's going to happen every time. You can work this out with xi's and mu's and the symbols, and that will always happen. So it's not a good idea, or it was a good idea until we got this encounter that some are negative and they're always going to get a 0. So one way we can address this is, well, let's not talk about the differences or the distance. Sorry, not the difference between values and the mean, but really distances. And when we talk about distances, maybe we're talking about the absolute value, right, of the difference. So take the absolute value of these deviations. Now they will all be positives, and if you add them positive, a 3 plus a 3 is a 6, plus a 1 is a 7, plus a 7 is a 14. So this is called the mean absolute deviation. It's a bad abbreviation, MAD, but bad acronym. But that would be called the mean absolute deviation, and the example would be 14. Now that is useful in some contexts, and it does give you a correct meaning. Yeah, this is an average. How far is each data point from the mean? But that's not the one that we use the most. Okay, the one is very useful is going to be called the standard deviation, which is just the square root of the variance. We'll see that in a minute. So the variance is instead of going this route to where we took the absolute values, we're going to go on a different route where we're going to square each of these quantities. Yeah, so instead of considering a -3, we're going to have a positive 9, a positive 9, a 1, a 1, and a 36. Yeah, so it will give you larger numbers, but it's going to be useful for something we'll see later. So we're going to have two definitions. This is going to be called different, similar to what we did with the mean, if we had the population mean or the sample mean, two different symbols. We're going to have the population variance and the sample variance. These are squared because the definition we want to get to is the square root of these, and that's going to be the standard deviation, okay? So the variance is this symbol that is sigma. This is just a Greek letter, sigma. It looks pretty curly in my font that I use, but it's just the symbol. You've probably seen something similar to that. It's the lowercase of the one region for the sum notation, but it just means the standard, sorry, in this case, sigma squared is the variance. So the variance would be the sum of all these deviations squared divided by the number of data you have. If you're talking about the population, and if you have the data from a sample, it's going to be called the sample variance. And it's similar, but you don't divide by the data number of data you have, you divide by n minus 1. Okay, so this is important. In the mean, we had two different definitions, or two different symbols, sorry, but the same definition. We just add all the data and divide by how many you have. If it's coming from a population, we call it the population mean. If it's coming from the sample, we call it the sample mean. But here, it's not only that we call it different, the formula is slightly different. Okay, you have to be careful about that. Here, we are dividing by n. Well, here, we're dividing by n minus 1. And some problems in your homework and your assignments might be not totally correct if you're using the incorrect formula, okay? You have to be careful if the data you're working with comes from a sample or from a population. Now, why are we using n minus 1 and not n? There's not really good explanation at this point. The only thing I'm going to say is that if we have only a sample, we are approximating, right? We're going to use that like our goal to approximate the real standard deviation. So we rather overestimate than underestimate the standard deviation. For some reason, that might make sense a little bit later. So in that sense, dividing by n minus 1 gives you a bigger number, right? Overall, this quantity is bigger than this quantity if you had divided by n, right? Because a larger denominator makes the whole quantity smaller. Okay, so that's all I'm going to leave it right now. That's a little bit of an insight of why that would be it. Okay. Okay, so let's go back to this example that we did at the beginning where they have 10 scores from an algebra exam. I use this data to find the range. How do you find the standard deviation? Well, I need to find the mean. We already have that from a previous work. It's 71.6. This is work that that we do that makes sense to do in a spreadsheet, right? So that's why sometimes we emphasize that, well, just do it in a spreadsheet. But even if you're doing it by hand in an exam and you don't have access to a spreadsheet, or we don't want you to do it in a spreadsheet, and because we don't want you to do it in a computer and in exams, they keep things organized very nicely if you keep things like this. So I write my data sets in a column. This could be or not be written, the column for the mean, since we're going to do it. But you know that what I'm doing that is because then you're going to subtract every row, right? 80 minus 71.6. And that's an option you can do by rows in a spreadsheet. And these are the deviations, right? When you get those differences. So you do it in the first row, you paste the formula, and it does that. Then each row, each value here gets squared. And so this is something that, remember where we got this, why we squared them. We wanted to avoid the fact that some are negative and some are positive. And if you added these, you would get a 0. So the whole point of squaring them is that we positives. We want them to be positives, or give us some measure of it without getting a 0. We could have used absolute values, and we said that works, but this is going to be something different, but it also gives you a measure of how dispersed the data are. And so my point is, these quantities have to be positives, okay? I've seen students that when they do these tables, for some reason, these numbers show up negatives and it doesn't make the results correct. And of course, it's wrong. You're squaring a negative quantity, which means you multiply negative 4.6 by negative 4.6, so you get a positive quantity. So then you add these numbers, and that's something that is easy to do again in the spreadsheet. And I'm almost there. Then I take the square root. Sorry, this is coming from a sample, so I need to divide by n minus 1. I had 10 data points, so I divided by 9. And this is a sample standard deviation. Okay, so this is it. If I ask you to find, if a question asks you to find this is the sample variance. I haven't taken the square root. So now define what the standard deviation is. It's the same symbol as before. It's a sigma for the population standard deviation. It's the S for the sample standard deviation. And so just take the square root of the number we had, and the standard deviation for this example would be 16.568. There's no rule of how much to round, but I guess in our textbooks it will tell us how much to round. In quizzes and exams, if you do work correctly, it will be graded accordingly, and it's not a problem. We do have to know that you have to have a few decimals, 2 or 3 always, but there's not going to be like a rule of thumb that everything has to be the same. But you shouldn't say that the standard deviation is 17. Okay, it's 16.5 or 16.6, sorry, or 16.57. One thing to notice is that the standard deviation has units, the same units that we were working with. Why? Well, I had, where's it coming from? Each xi in this example that I did was years old, or number of years. When I subtracted from the mean, that's a difference of years, so it's still years, the quantity. I squared it. That unit doesn't make a lot of sense, but it's years squared, right? Then you added them. You add in a bunch of years squared, it's still the same units. You divide by a number, right? The number in the bottom is how many data you have. Sorry, in this case it would be n minus 1. It doesn't matter. It's a number, so it doesn't change the units. It's still years squared. And the last step, you take the square root, so you go back to years. So we can say in this example, where there were grades from, in my example, there were grades score from points from an exam. So the mean was 71.6 points, with standard deviation 16.568 points. Yeah. If there were ages, this would be I can say the mean of the population of all students at the college is 29.6 years old, with standard deviation 3.6 years. Okay, so hey, the standard deviation has units, and it's the same units as the data itself. Okay, I'm going to finish this short video with what are we measuring with the standard deviation? Well, the mean gives you a measure of the center, right? Like I said, if I give you the average of a grade of an exam with 71.6, you have something. But the standard deviation gives you a measure of how spread the data is. So if you think about it, the values that are far from the mean contribute a lot for that sum, right? Like for example, in my numbers over here in my table, you can see that the numbers that contributed a lot to the sum were the ones that were far from the mean. So every time you have a number like 93 that was far from the mean, the difference from the mean was 21.4, right? And then when you square that, it becomes 457. So that's making this total big, right? The numbers that are close to the mean, like let's see, they're not really well. 67 is close. It's 4.6 points away from the mean. When you square it, it doesn't get that drastically bigger, right? So the numbers that are far from the mean, like the 45, for instance, doesn't matter that it's negative. 45 is far from the 71.6. When you take the difference, it's 26 units away. When you square it, it gets very big. So for every number you have far from the mean, it contributes a lot to the sum, it's going to make the standard deviation larger. So a large standard deviation tells you that you have a lot of data away from the mean. A small standard deviation means most of the data, or you have a lot of data clustered nearby the mean. Yeah, so that's what the standard deviation is measuring. It makes a lot of sense when you compare two data sets with the same mean and different standard deviations, you know which one is more dispersed. Okay, so I have some pictures here. This one is a good example. This one we have a larger standard deviation, like I was saying, because all of these are data points that are away from the mean. The mean would be somewhere here in the middle, right? Because these will average to the middle for every point you have on the edges. On the other hand, here there are a lot of that data in the middle, and that's going to be contribute very little or nothing to the sum, right? Because these are very close to the mean. And the numbers that are away from the mean, they're not so many, right? They're at least frequent. So it will contribute less to that sum, so the standard deviation would be smaller. In this example, I made 3 where I calculated the mean and standard deviation. So they all have mean 10, and the standard deviation is calculated right there. So this one has standard deviation of 2.09, and I said, maybe here the mean, maybe there is no data point that has value 10, right? So every value is away from the mean in some sense. Here, maybe these values are equal to 10 or close to 10, so they don't contribute a lot, and they're very few away from the mean. And over here, most of them are in the value of the mean, and there's very few outside. So the standard deviation is the smallest for that one. Okay, so that's how you interpret a little bit the standard deviation. I'm going to stop this video right there.